via the same tool, so stay tuned for that at the end. And so for today, we are going to take a deep dive into some common performance mysteries. And we have two performance engineers from D2L here with us today who are very excited to talk more with you about queuing and performance testing. And I will turn it over to them to introduce themselves.
So thank you very much, Tina, and hi, everyone. As mentioned previously, I'm Nicola Gordon, and together myself and Ioan Matei, my co-presenter, are D2L's performance team. And as mentioned as well, today we are presenting a queuing deep dive. So this is a topic that's on our minds a lot. In fact, as performance engineers, it's why we're here. All the metrics we collect, everything we investigate, and everything we report on is either directly or indirectly about processing time and about time spent in queues waiting to process. So with that insight into why Ioan and myself enjoy a good queuing discussion, let's get started. Let's talk about why queuing matters to performance. So these are the topics that we'll talk about today. We'll do what we call a queuing deep dive. But note that this deep dive is within the context of the short time that we have available today. We'll start by aligning on some high-level concepts, and we'll also introduce Little's Law to understand how and why queuing happens. After that, we'll focus most of our presentation on what we call performance mysteries. So we'll talk about CPU processing with a focus on what's going on at the queuing level. We'll talk about how to recognize an issue from a hardware perspective, how to investigate, and how to solve. And because performance issues typically result in infrastructure-focused solutions, we'll also talk about the bottom line, the cost. So Ioan will also share a short bonus topic towards the end of our presentation. It's a step away from that purely tech queuing discussion, but we wanted to show you one method we at D2L use to generate performance-related insight as part of our nightly regression tests. And lastly, we'll conclude our presentation with a review of why queuing is such a hot topic. In fact, we believe the hot topic of software performance. So, also, please note the disclaimer. You'll see lots of metrics in our presentation, but please note that nothing is in any way directly related to the performance of D2L's Brightspace product. So, Ioan will now go ahead with a queuing deep dive. And thank you, Ioan.
Hello, I am Ioan Matei, and we are starting with the deep dive, which obviously will be in the context of the time available for the overall presentation. We will go through a couple of key concepts, and we'll introduce the fundamental law of queuing, Little's Law, which helps us understand why and how queuing happens. We'll start with describing a few queuing fundamental concepts. The node, the processor, the bottleneck, and last but not least, the queue. The node is a component of our system that includes a processor and a queue. And if a queuing system has been implemented, the capability to manage queues. The processor is any part of our system that supports processing or serving of requests. The most obvious examples include CPU, disk, and network. The bottleneck is what is causing our response time to take a longer amount of time than the baseline value. The queue is the method used to manage and mitigate the limited capacity of the processor. For example, if processor utilization spikes to 100% to serve each request and maintains that 100% utilization at its full capacity, then queuing begins as the processor will eventually become overutilized. So the network of processors traversed by a request are that component of a system that determines the baseline response time. Queues may or may not factor into the response time, but as load increases and queuing starts, they account for that variable and escalating component of the response time. Now, let's discuss about a basic but important and quite common real-world example. Let's imagine a school situation during the summer. A student sends a login request, the web server processes that request, then the DB server processes the corresponding request. The student gets the response time in, let's say, a time of 1 second, which effectively is the duration of processing. Now consider the semester start of this year, Monday morning at 9 a.m., which is a very, very busy time, especially this year when everybody is going online. Again, the student sends a request. The request gets to the CPU where it sits in the IO queue, then in the network queue, and finally is sent to the database for a similar round of queuing and processing. This time, the student gets a response in a total time of processing, which is 1 second, plus all that queue time just mentioned. So we can talk here about the 6 things that matter. First of all, we have 2 request targets, the processor and the queue. These are the 2 places where the duration that is making up the response time is used. Therefore, we have 2 solution targets. And here is where we need to consider balancing one versus another. On one side, we have time on the customer side. And on the other side, which is the server side, we have the processing power, which I will translate. What it means is cost to solve the issue on the business side. And this is how we get 2 core business targets to consider in balance. But for now, let's detour a little bit to allow us to present Little's law. This is the fundamental law that we use for understanding how and why queuing happens. In a nutshell, what it says is that the number of requests in a node, on average, is a factor of the arrival rate of those requests and the average time it takes to process a request in that node. Queuing begins when the number of requests in a node is greater than 1. That is when requests arrive faster than they can be processed. And let's have a look at the next slide to visualize the concept that we were presenting until now. To exemplify Little's law, we'll assume that we have a closed model, processor and queue, where processing a request will take 100 milliseconds for all requests, and requests are coming in orderly fashion and at constant time interval. We have requests coming in on the left, the blue lines, and processing depicted over the green area, while the white area shows where queuing can fall. Scenario number 1 exemplifies when the system utilization is low. Here, our users are logging in at a pace of 5 requests per second, meaning that the arrival rate is 5. Little slow tells us that the average number of requests in the node is 0.5, therefore smaller than the processor capacity. The processor is used, but only half of the time. There is no queuing happening. Scenario number 2 exemplifies when the system utilization is at par. The arrival rate increases to 10 requests per second. Little slow tells us that the average number of requests in the node is 1. We have on average 1 request in the node at any given time. The processor is fully utilized, but continues to be available immediately for every arrival. Still, there is no queuing happening, as each request coming in goes directly into processing. So the CPU is 100% utilized 100% of the time. It processes a request, completes, and immediately starts processing the next one. We must remark here that as long as queuing is not happening, again, on our closed theoretical system for now, the response time is both consistent and predictable. And now we have scenario number 3, which exemplifies when the system is overutilized. That is the point where number of requests in a node is greater than 1 and queuing begins. In this case, we have 20 requests coming in 1 second, and we will start to have queuing happening into the system. Into the next slide, we will zoom in to see what can happen in this situation and to understand why we end up with queuing forming up. So let's keep our eyes on the white area. Here on top, we are showing the arrival rate from scenario number 1 and number 2. In both cases, the requests go directly over the processor and are processed right away. Our users are experiencing our baseline response time in these 2 scenarios. Now, on scenario number 3, we have 20 requests arriving within a second. So that is 1 every 50 milliseconds. And we can see them starting to queue up here on the white area, which is reserved to depict the queue. For the first request, which is processed right away, it takes 100 milliseconds to complete. Therefore, the second request will have to wait 50 milliseconds and then is processed within the baseline processing time. So for the second request, the total processing time is 100 milliseconds processing time plus 50 milliseconds queuing time, which is ending up to a total response time of 150 milliseconds. As the third request hits the system, when the second one only starts to process, it will wait for the entire second request to finish processing before itself it's processed, and will have a total response time of 200 milliseconds. So the bottom diagram is intended to give an illustration of how a regular arrival rate can escalate into an increasing response time over time. Unless the processor has time to recover some gap to complete processing, the queue will have to deal some gap to complete processing the queue, I mean, we will have to deal with an increasing response time, which is depicting over here. Now I will present an example that illustrates what we just mentioned. That is, as the arrival rate increases, we potentially end up with escalating response time. This particular scenario presents a number of login iterations, 10, all synchronized to execute at the same time by our load. As you can observe, the response time for the first login is faster or lower, depending on your preference. So this is faster than the last. We see here the increase in response times. The first time is just the time it took to process the login request, and then as the other requests join the queue behind the first one, the response time escalates until each one moves through the queue and is processed. Then what you can see here are a number of iterations executing the same request. Obviously, there are quite a number of factors in the system affecting the response time, but as you can see, we get the same profile, which is indicative of a queuing issue. Now, directly underneath, we can see that as the requests are issues, the processing starts and the CPU usage increases. And as the CPU usage increases, the processor queue length increases. As the requests are processed, the CPU usage is hitting 100% and the queue is growing, meaning that the CPU is overutilized and not able to immediately handling any other request that comes to it. So to summarize, when we have a synchronized arrival rate, we will encounter a growing queue, which will result in an overutilized processor, which can cause an exponential growth in response times. We can see here what can happen when we are gradually increasing the number of requests being sent to the system over a longer period of time. And we are talking about the hockey stick effect. The response time is escalating when there is a lot of load hitting the processor, and as more requests join the queue, the response time increases. So having a sustained arrival rate results in sustained growth in response time, and we have a potential impact to our customer SLAs. In this happy part of the graph, we can see consistency in response times. When there is minimal or no queuing, the response time values don't vary much. As soon as queuing starts to grow, we start to get unpredictable and unwanted results. As you can see here, both we and our customers are happy, while up there, we are not so happy anymore. And now it will get even more interesting. I will hand over to Nicola to uncover some noteworthy facts connected with what we discussed until now.
Thanks, Ioan. So as you're finding out, Ioan and I love a good performance mystery, but we love it even more when we find the solution. This section of the presentation is going to dive into a typical performance mystery and we'll use our understanding of queuing to come up with some solutions. First, let's start with some background on where we might see queuing-related bottlenecks before we move on to an example. Infrastructure resources is, let me just get my laser. Infrastructure resources is the first place we generally target when we start an investigation, and as well the first place we typically target when looking for a solution to a bottleneck. Some common infrastructure places where you can encounter bottlenecks are the CPU, the disk, the network. For CPU, for example, a queue maintains a list of requests waiting to be processed and processes them according to the CPU's scheduling algorithm. Note that in this case, as with following cases, the bottleneck is the processor, not the queue. Bottlenecks can also occur when software configuration limits are imposed. In this case, assuming a queue exists to manage traffic to the resource, the request joins the queue and will be processed as the limit clears. In this case, the bottleneck is the resource that is limited by configuration. Queuing can also be implemented through software, for example, as message queues. Once again, the resource that takes items off the queue is the bottleneck. Note that both configuration and software bottlenecks are a symptom and both point directly to the hardware processing capacity. So these items here as the source. Or put another way, if requests can be processed more quickly, there'll be less chance of hitting a queue. So to summarize, any resource that processes a request has a limited processing capacity and has a queue implemented is a place where bottlenecks can occur. Now let's take a look at a real-world example, coming back to the scenario where request load reaching a limited resource is increasing over a period of time. We experience what Ioan referred to earlier as the hockey stick effect, where past a certain threshold, the response time escalates abruptly, and we have a really clear indication of a performance problem which needs to be investigated. And this is illustrated over here. The y-axis shows increasing load in requests per hour, and the x-axis shows elapsed time. The gray line shows incremental load, and at some point the processor is no longer able to keep up, and an occasional small queue that is regularly cleared transitions to a persistent and growing queue, somewhere around here. At that point, response time, shown on the secondary y-axis, escalates rapidly, and we see vertical bars that represent high response time over here. In the next slides, we'll look at how this can be investigated along with some solution strategies. So we've talked about a couple of places where you might see queues in your system. This points to the first step in analysis. We need to identify the bottlenecked resource. Windows performance counters are our go-to method of getting that direct insight. So in that case, let's take a look at the Windows Performance Monitor, and here's what we'll see. We'll see an indication of percent utilization or count up the y-axis. We'll see elapsed time along the x-axis. And we've added counters for network, disk, and processor queue length, as well as percent processor time, which gives us some additional really important insight. And what we can see here is there's no queuing showing for anything other than the processor. There's no indication of these two blue lines for network and physical disk on the graph. But for the processor, with few logins initially, there appears to be minimal queuing that repeatedly clears. So queue length, the red line, repeatedly drops back down to 0. As incremental increases in load are applied, so looking back at this previous graph, we're seeing we're going from here to here. and we'll shortly increase load to here. CPU escalates. We don't see much changing with the queue length down here. Then an additional increase in load, again as shown on the previous graph, increases CPU utilization to close to 100%, and at that point, the queue can't be cleared any longer and it starts to grow. So now we know that the root cause of scaling response in this case is CPU queuing. The processor is processing too slowly to keep up with the rate of newly arriving requests. In that case, what can we do with this insufficient processing capacity? We can, of course, reduce queuing by throwing more hardware at the environment. So let's throw more hardware at the environment. So the initial hockey stick effect you saw previously is now shown here as the yellow line with a test running on a single processor. On the y-axis, we have increasing login requests per hour. Along the x-axis, we have increasing response time. And at some arbitrary load of 21,000 requests per hour, on a single processor, we see a pretty slow response time of about 8 seconds. Back to that question. In order to solve this on a static code base, what can we do? So let's hypothesize that scaling CPU processor capacity will do it. We could scale out, scale up, or we could use a faster processor. In this case, we'll scale out from 1 to 2 processors, and we see response time is much faster. It decreased from 8 seconds down to about 1 second. And just for fun, we ran the same test with 8 processors, and we can see that the response time now is about 200 milliseconds at that same load. So our hypothesis was verified. Increasing hardware at our environment, i.e. throwing more processing capacity, improved our result. So let's try to visualize that relationship between response time and CPU count. And I'll start by apologizing for how busy this graph is. I know there's a lot going on here. So the base components are the same as for the previous graph. We have increasing response time along the y-axis. We have increasing load along the x-axis. We have the 3 curved lines that show 1, 2, and 8 processors that were used for the test runs. And we have that arbitrary load of 21,000 requests per hour. The added data points, the vertical bars, represent CPU usage as measured by the secondary y-axis on the right. So let's focus on that arbitrary load again. As you've seen, at 21,000 requests per hour, a single processor takes 8 seconds to process. And if we follow the related CPU bar up, it's difficult to see, it's under the red line and stops about here. We can see that it uses about 90% of the CPU's processing capacity. So we can see why we have response issues. That single processor is almost always busy and is likely serving a long and growing queue of requests. At the same load, 2 processors, the blue line, takes 1 second to process, as we've seen previously, and following the blue CPU bar up, it uses about 50% of the processor's processing capacity. We can see why response time is improved. At less CPU, we have less queuing, and a shorter queue means less time waiting to process. So no need to repeat the evaluation for 8 processors. Instead, note that response time is steady to a much higher load. Until CPU starts climbing fairly high, we don't likely have much queuing, and response time is likely close to the baseline processing time. So I know that was a lot to digest. At this point, I just want to do a quick recap to summarize the steps we've taken so far to analyze. So we noted the hockey stick effect with rapidly escalating response time and realized that we have a bottleneck. We monitored queuing at some key resources and determined that the queuing was CPU queuing. We hypothesized and verified that additional processing capacity may solve the issue, and shown on the current graph, we aligned reduced CPU utilization with reduced response time. So there will be time for questions at the end, but I believe we have our question link open if you want to start. You wanted to add any questions just to keep track of anything related to the points to this point. So the current conclusion here is about processor utilization. That's just the symptom though. So what's the source of this issue? Spoiler alert, it's queuing. So with that in mind, we know the total time for a response is the time spent in the processor plus the time in the queue waiting to be processed. So looking here, same graph as previously with response, load, 1, 2, and 8 processors, and that arbitrary load. The difference is we've now replaced that indirect indicator, the CPU, the symptom, with the cause, the queue length. So bars and secondary y-axis now represent queue length instead of CPU. So at that load of 21,000 requests per hour, 8-second response time is seen for a single processor, and the processor queue has, following the yellow bar across, about 30 requests waiting to be processed. And for that same load, a much reduced 1-second response time, following the blue bar across, there's about 5 requests waiting to be processed. So now we've confirmed that the root of that slow response problem that we solved by increasing processor count was a queuing problem. So far we've talked, all we've talked about is throwing more hardware at the problem. And that's a great solution when you have a static code base or when a critical performance event happens that needs to be resolved quickly. But the hardware solution should not be used in isolation. With that in mind, the complete solution to our response time / queuing problem is to reduce the time to process by either processing faster or processing less. As seen previously, we can increase processing capacity by increasing processor count, size, or speed, and that aligns with increasing from 1 to 2 to 8 processors. Or we can configure to increase processing capacity, for instance, by increasing thread count, DB connections, or Lambda instances. The graph, as we've used it so far, is about hardware, but I'm going to reuse it to also illustrate this point. For example, we could also process faster by configuring from 1 to 2 to 8 Lambda instances to process our request. And for the last solution, we can consider optimizing our software. Instead of increasing the capacity available to process our request, this method decreases the amount of capacity required to process the request. And it does that by decreasing the number of low-level instructions per task. This one moves backwards. Queuing, and therefore response times, are decreased by decreasing the number of instructions required from 8 to 2 to 1. A short aside here, note that task can refer to either an individual request that can be optimized for instruction count or a group of requests. In particular, consider repetitive operations such as looping and recursion, where request counts can really escalate. And just an aside, the tool we use at D2L for that code level insight is ANT's Performance Profiler, and we use it to pinpoint really quickly where request is being called many times. So that comes in handy for Ioan and I on lots of occasions. So we've concluded that we have 3 high-level solutions to queuing, i.e. hardware, configuration, and software. Let's take a very short detour to consider how various solutions can impact the bottom line, the cost. We'll take a short dive first into a hardware cost analysis. So let's find out what it costs to use a hardware-based solution to resolve that hockey stick effect. Or at a lower level, what does it cost to reduce response time by reducing queuing? So on the previous graphs, we chose an arbitrary load. Let's look at this instead from more of a user experience perspective. So let's imagine that we have contractually agreed to a maximum 2-second response time for a particular request. Sticking with a max of 2 seconds, we can support load here, here, and here. That's 14, 25, and 43,000 requests per hour on 1, 2, and 8 processors while maintaining that 2-second SLA. Or interpreting this another way, we'd like to evaluate what it costs to support, for example, a small, medium, or large customer within their SLAs. So we saw that we can support small customers at that 14K requests per hour with a single processor. Assuming that single processor is a T2 small at standard pricing over the course of an entire year, we can support that customer with a cost of $564 for their app server. And that's the small customer. And if we follow the line up, we can note escalating costs to maintain the 2-second SLA for a medium customer and for a large customer. Now let's talk about context, because metrics are useless without understanding the context. These numbers are based on one particular request with a whole lot of additional context required to really align with a particular scenario. So the takeaway here is what matters, i.e. we can support a certain load at a certain size CPU or processor count that effectively reduces queuing and that aligns with cost. So we've seen hardware, configuration, and software methods to reduce queuing and decrease response. Let's keep in mind all of those come with a cost. So the easy cost indicator is the hardware. That's an upfront cost. We know that throwing, for example, another T2 instance at the problem costs more. Software optimization and configuration come with longer-term costs, though, in performance engineering time, developer time, and time for anyone involved in doing that optimization. And to conclude the section of the presentation, there's no one-size-fits-all solution. Performance optimization benefits most from a holistic approach that considers the cost benefit and architectural feasibility of each solution, and usually results in some hybrid implementation of those options. So that's it for solution cost, and Ioan will now take you through some quick insight into D2L specific performance workflow.
Thank you, Nicola. And now for the bonus part of our presentation, we'll spend a few minutes to briefly talk about our performance engineering tooling. We are using the performance engineering tooling at D2L to support exercising load for queuing insights and understanding performance profiles and other performance behavior and issues. Our main process is based on JMeter, Jenkins, AWS, plus other internal infrastructure tooling which is specific to D2L. A quick word on JMeter. JMeter is an open source load testing tool for analyzing and measuring performance of a large range of services with a focus on websites and applications. It is an integrated tool supporting scripting, designing, and running a test scenario and reporting. It also accepts a multitude of external plugins. This is a brand new tooling at D2L and still evolving. And while to date it's used only by the performance engineering team, it was designed and built to be available to a wider audience for specific tests depending on the specific needs. We'll present now a high-level view of our testing process flow. We are using Jenkins to spin up the testing environment according to the testing needs, and we run the test scenario using JMeter. With JMeter, we are using a set of test scripts comprised of mostly Selenium JavaScripts to simulate real end user behavior in a browser session, but we are also using HTTP request samplers. Simulating end user behavior is quite nice, but is also quite taxing on resources. And here is where our ability to leverage AWS EC2 virtual machines option comes in very handy. Test results are compiled, displayed, and stored in AWS, where they can be easily accessed for They can be easily accessed for further investigation and comparison with previous test runs. We are also making use of PowerShell scripting and perfmon performance counters, as JMeter has limited native measurement collecting support. Recently, we added another tool in our arsenal. It's the ANS Performance Profiler, which we use for profiling expensive database queries and insights on performance bottlenecks on the .NET code and the data access layer. And to conclude our presentation, we want to share why it matters. From today's discussion, we could see that we can reduce the response time by reducing queuing times. We can target the solution with a hardware configuration and software optimization, keeping in mind that performance optimizations benefit most from a holistic approach that considers the cost benefit and architectural feasibility of each solution. And in this way, by improving our users' product experience, we can also support D2L's North Star, which is to help transform the way the world learns. Before going into the Q&A part of the session. Allow me to thank you for attending our presentation. Both Nicola and I hope that we unveiled in this session some of the mysteries underlying performance engineering and systems behavior, and systems behavior and performance under certain demanding conditions. And now, please feel free to ask any related and unrelated, if you want, questions. Thank you.
Kyle, I can't hear you. I see you talking though.
Maybe now. There we go.
I do hear you, yes.
Thank you. Thank you both for your presentation. And I'm going to switch over to share my screen where we've been queuing up some questions.
You said queuing up questions.
Unintentional, but I really wish it was intentional.
We'll take it.
Exactly. So the first question that we have is, thanks for your insightful presentation, excellent and relevant. Can you recommend books or training materials for software engineers learning queuing theory?
Yes, actually, there was an excellent book that that I read when I started out, and Ioan has read as well, when we were starting out on really diving into queuing. I don't have the name offhand, although I'll say that I have been looking at it recently, but the actual name, Ioan, do you have the name offhand?
Not right now, but I know it's a Russian guy that presently or recently worked for Oracle Corporation or did some consulting there. Yeah, give me a second.
Oh, I've got it now. Okay.
Oh, yeah.
Sorry about the delay. Solving Enterprise Applications and Performance Puzzles. And it's by Leonid Grindspan, something similar to that. So I'll be honest, that was a fantastic book. It summarized things really well. It broke things down into this simplified model that allowed you to kind of grasp the concepts, and then you can think about that bigger picture of how it aligns with the real system. So I would highly recommend that book as a good starting place.
Thank you very much. The next question that we have is curious if you have any insights on performance testing in the world of cloud computing and its ability to automatically scale based on performance metrics.
Yeah, I can comment on that. All of the work that we do at D2L is using AWS cloud services, and absolutely essential for getting that high load insight. So we use and Ioan, I guess if you guys can recall the slide that Ioan showed. We use EC2 instances and JMeter. And if we use JMeter that's using Selenium, we can hit the server directly. So we're not using up tons of resources on the controller, and we can scale our load really high. And that's a large component of how we get the high loads. And then of course that image showed further on that the automated visualization was a really important component as well. Is everything goes through S3, Athena, and into QuickSight, and we can visualize what those high-load tests look like using that method. And as Ioan showed as well, you can see it even gave us some insight into a specific queuing scenario. So yeah, that's the tool that we use throughout D2L, AWS, and with performance engineering is absolutely essential for those tests.
Thank you.
Just want to add here that as a performance testing team, we are focused quite a lot of testing, first of all, real scenarios, also testing other scenarios and scaling up, let's say, scenarios that can happen. And the flexibility of AWS comes in quite handy. Also, maybe this will relate also to the question. We have an operations team, a network operations team within the company that also takes care about the day-to-day operations, and they are using some performance metric from QuickSight that helps them with scaling down or up, depending on the necessities of the day or the client.
Yeah, and we've watched that in action, and it's absolutely amazing to watch how it seems so powerful. So you have a customer who's using a lot of resources, and you can see that very quickly it's recognizing the thresholds it's hitting, it's scaling up using auto scaling groups, and as Ioan said, scaling down again. So it's pretty cool to actually see it in action.
That's great, thank you. The next question that we have is, who did you share these results with, and what was their response?
That's a really interesting question. So our tools can detect queuing, as shown on that final slide with Ioan. It can show that we're having some response times that are escalating throughout the time frame of a test. The presentation today was based on thinking about a story that we wanted to tell, and then making our load represent that story. So as far as the results that you saw today, this was about telling a story. If we saw those results in real life, then this would be a discussion. First of all, in our tool that we manage our defects, we use Rally, and it would go directly to a developer. It may go to an infrastructure person, and there would be those direct discussions around how we produced it, how they can reproduce it, how we can support any effort they have in diagnosing the issue, whether it's diving into the queuing directly or whether it's diving into the code and just knowing how the code works.
That's great, thank you. I'm just taking a look at our time here. We still have a few more minutes left. The next question that we have is, can you talk about applying a back pressure, especially in situations of having queues somewhere inside of a network of microservices?
So I'm not too sure what applying a back pressure indicates. Is that something that you can expand on? I'm not sure if the people who ask the questions are able to.
I think this refers to maybe, let's say, responding with back force, sort of, to the flow of the data and of that adds in the queue.
Yeah, and I wonder, for my limited experience of performance testing, I wonder if maybe it's creating load on a system already inside the queue to kind of create a kind of like a negative pressure situation where you might cause queuing to happen more easily.
Yeah, and I think as far as causing queuing to happen, that's something that we can, I mean, when you know what resources that you have available, whether it's in your core product or whether it's in one of the microservices, if you know what resources they hit hard, then you can, and how that happens, and you can try to simulate that. As with any case of queuing and bottlenecking, if you remove the queue or the bottleneck in one place, for example, in one of the microservices, what you're probably going to do is you're going to open up the opportunity to experience queuing somewhere further down the line, whether it's another microservice or whether it's in a core product. And that's what that tuning is all about, is constantly looking for places where you can remove that queue and open up an opportunity for a different resource to be hit faster that wasn't necessarily being fully utilized, and then looking to reduce the queuing there as well. So Michaela, I hope I answered your question.
And yeah, and thank you for taking the time to figure it out and to provide a response back. The next question that we have is, do you use any tools to help you diagnose queuing issues?
I think this is can be linked to the next one. It
Yes.
is ads, like in and with an S.
Cool. Well, let's jump to that one then. Let's jump to Mark's question. So, what was the performance profiling tool you had mentioned?
Ants Performance Profiler by Redgate. Fantastic tool. So we don't. So what we tend to see is more of a indication that there's a queue, and so a lot of those graphs we showed where you saw response time increasing, that's again the symptom as opposed to the cause. And we'll see the same thing in the Ants Performance Profiler is response starts increasing. You can see response doing this, in which case the processor is recovering, the queue is getting brought back down to 0. But if you see instead it's doing this and then it's doing this, yeah, it's your indication that there is some queuing that you need to look into. And to be honest, once we see that, more often it's performance counters that we'll dive into and start, okay, and that was shown in the slides, is, okay, let's take a look at a few of the likely places and let's start narrowing it down. And we can see that the CPU queue is growing, for example. So often our work is a bunch of tools that we bring together to answer different parts of that question.
Also, such a tool helps us when we go back to the developer to discuss about solutions. Let's say this is making the system to us from a black box more gray, so more transparent for us, and it's easier and saves time on the developer side as we can go with more information rather than the classic response time and performance measurements.
Thank you. I think that's all the questions that we had for today. I'm going to open up a couple of polls just to, so we can get some feedback. So there's going to be one poll, which is, so people that are on the call, please use Slido. There's an event code there that you can type in. There's also a link in chat. There's a couple of questions that we have. One is, what feedback do you have for our presenter? And the other one will be just rating today's meeting on a scale of 1 to 5. If people could fill that out, I'm going to leave it open today just so that we can collect that feedback. Thank you very much both for your time. Tina, I don't know if there's any closing remarks that you have that you want to make, but I'll stop my sharing here.
Yeah, no, I think that's good. Thanks for managing the Q&A, and thanks very much to Nicola and Ioan. I learned a lot, and I hope the rest of the audience did too. We appreciate your time.
Thank you. You're welcome. It was a pleasure.
Thank you.
See everyone next month at the end of October.
Sure.